the fabulous perfect spring, a device that causes motion which is both perpetual and simple harmonic. Well, it's those properties of the perfect spring which make it ideal for use in mathematical modeling. And in this program, we're going to use it to gain some understanding of simple harmonic motion. Now, armed with this understanding from a theoretical model, we'll then go on to study real systems, such as the ones you'll be seeing in the text. Well, you already know from the text what the differential equation for the perfect spring is. It's given by mass times acceleration is equal to force. Now, what is this force? Well, K here is a positive constant, which is just the stiffness of the spring. L0 is just the natural length of the spring, and X is just the position of the mass at the end of the spring. Now, this differential equation is good whether we have extension or compression. It's good throughout all stages of the oscillation. Well, what about the solutions to this differential equation? Well, that depends very much on the initial conditions. You can see what the solution looks like if the spring is stretched and the particle released from rest. This shows how the position of the particle varies with time. It's simple harmonic. This is the solution for the initial conditions we used. The general solution to this differential equation is of this form. X is just a cosine function of time. Now, what about these numbers which occur in the solution? Well, omega and L0 are just numbers which are intrinsic to the system. For example, L0 is just the natural length of the spring, and omega, well, omega is the angular frequency measured in radians per second, and omega is given by this expression, the square root of k over m, where k is just the positive number, which is the stiffness of the spring, and m is just the mass at the end of it. And that determines what the period is. You see, because this is a cosine function, it repeats itself every 2 pi, and so every time t changes by 2 pi over omega, we get back to where we started. So the period is given by 2 pi over omega. And I can represent this as the period. Now, that period is the same for large oscillations and for small oscillations. It doesn't depend how we set the system in motion. And that's a very distinctive feature of simple harmonic motion. Well, what about the other numbers which occur in the solution? Well, they do depend on how we start the system in motion. A is the amplitude. It tells us how far we get away from the natural length from the static solution, and that really, in this case, depends on where we start off the mass in motion. Phi, well, phi is called the phase. It's measured in radians, and that really tells us how the motion started when t equals 0. So again, the phase depends on the initial conditions. In this case, phi is 0. And here phi is pi by 2. Here are two solutions that differ only in phase. Remember, for the left-hand system, phi is 0, and for the right-hand one, phi is pi by 2. Each system oscillates in the same way, but at a different time. So the difference in phase expresses how far out of step they are. So now we know all the features of simple harmonic motion as predicted for the perfect spring.
Unfortunately, I haven't been able to get my hands on one of Alan's perfect springs. That's not too surprising because they're really only a figment of his mathematical imagination. In the real world here, no spring can keep an object oscillating forever. But we can understand quite a lot about real spring mass systems by using Alan's model. I shall model this object by a particle of mass m, and this real spring by a perfect spring of stiffness k. Now, thanks to the air track, there's no other force that I have to bother about. And so the prediction is simple harmonic motion with a period determined by m and k. The period is independent of the amplitude. And what's more, the period is just the same for vertical oscillations. The constant force of gravity has no effect on the angular frequency. The only difference is that the spring is extended in the static position. To change the period, I must change the mass or the spring. And an increased mass gives an increased period. The angular frequency goes down. If the spring stiffness is doubled, we get the opposite effect. And combining the effect of increased mass and increased stiffness gives a system with the same period as a single mass and spring. And that's still true even if I arrange the springs differently. Well, all those systems can be analysed in the same way, by modelling the springs as perfect springs, by applying Newton's second law and then solving the resulting differential equations.
But that's not the only way of analysing oscillating systems. You may remember from Unit 4 that when the force depends only on the position, some problems are better tackled using energy conservation rather than Newton's second law. Now, for our perfect spring mass system, the total energy E consists of two parts. There's the kinetic energy, which depends on the speed of the particle, and this potential energy function, which depends on where the particle is. The more the spring is extended or compressed, then the greater is this potential energy. Well, what is the precise form of this potential energy function? Well, it depends on the force F that occurs in Newton's second law. This is the general result from Unit 4. For the total energy to be constant, the potential energy must be just minus the integral of the force. Well, we know what the force is. It's just the right-hand side of our expression for Newton's law. In our case, minus k into x minus L0. So now when we integrate that expression, then we're going to get the following result. Now you see, that integral involves an arbitrary constant of integration, which we're free to choose. And surely a natural choice is to say that when the spring is at its natural length, then the potential energy it has is 0. And that involves in choosing that constant equal to 0. So this is our energy conservation equation for the perfect spring. Now, it involves the speed and the position, and it helps us to relate these things without having to go through a calculation involving the equation of motion and time. And really, that's the main virtue of the energy conservation equation. The total energy of the spring mass system is constant, but the two parts of it, the kinetic energy and the potential energy, are continuously changing. So let's have a look at that. In the static position, the potential energy is 0. When the spring is stretched, it acquires potential energy. This energy becomes the total energy of the system, which we've called E. Once released, the potential energy of the spring changes continuously throughout a cycle. The maximum value of potential energy is E. It reaches a minimum when the spring has its natural length. At this instant, the kinetic energy has its maximum value, which will be the number E, since E is the total energy of the system. In full compression, the particle is instantaneously at rest, its kinetic energy is 0, its potential energy E. Again, at the natural length, the reverse holds. So, at any instant in the cycle, the sum of the two energies must be equal to E.
So far in this program, we've concentrated entirely on the motion of a particle caused by the tension and compression of a spring. We've modeled this real spring by a mathematical idealization called a perfect spring. The characteristic of the perfect spring is that it exerts a force which is proportional to its extension. Another way to think of this is that the potential energy stored in the spring is proportional to the square of its extension. Now, the motion of a particle on a spring is oscillatory. And oscillatory motion is very common in nature and very important. For example, we're all kept going by the beating of our hearts and the oscillations of our lungs as they fill and empty. The transmission of my voice to you itself involves a chain of vibratory motions in my vocal cords, in the air molecules, in the microphone, in the loudspeaker in your television set, in your eardrums, not to mention the oscillatory currents in lots of electrical circuits and the oscillations of the electromagnetic waves carrying the broadcast. Now, these are all really much more complicated than the motion of a particle on a perfect spring. But to understand them, we first need to understand about the spring, because that's the simplest kind of oscillation. That's why it's called simple harmonic motion. And that's why we've been concentrating on springs so far in this program. But in the rest of the program, we're going to look at another kind of mechanical system which produces oscillatory motion. One familiar example of this kind of system is the pendulum. Before the invention of electronic watches, people used the oscillatory motion of a pendulum to keep time. But how does the period of its oscillations depend on its dimensions, on the mass of the bob, and so on? Now, the oscillations of a pendulum are not exactly simple harmonic, but provided that their amplitude is kept small, they're very nearly simple harmonic. By adapting the method of energy conservation, which Alan described for the perfect spring, we can actually calculate the period of oscillations of a pendulum. The trouble is that so far, we've dealt only with particles moving in straight lines, and the bob of this pendulum certainly doesn't move in a straight line. It moves along an arc of a circle. Nevertheless, in a sense, it's still one-dimensional. We need to specify just one quantity to determine the position of the bob. The position of the bob is completely determined by choosing an origin on the circumference of the circle, say here at the lowest point, and measuring distance of the bob from that origin along the circle. We'll call the distance from the lowest point Q. Applying the method of conservation of energy is a bit more complicated than in the case of straight line motion, but the basic method remains the same. The sum of the particle's kinetic and potential energies remains constant throughout its motion. The problem is to determine the kinetic and the potential energy. Now, as the bob moves, the variable Q changes. In other words, Q is a function of the time. And since Q is a length, its derivative with respect to time gives the speed of the bob. So the kinetic energy is calculated in exactly the same way as before. The potential energy here comes not from a spring, but from gravity. As the bob moves, its gravitational potential energy changes. What we shall have to do is express the bob's gravitational potential energy in terms of the variable Q which determines its position. Well, we'll come back to the details of how this is done in a moment. But there's one point I'd like to make straight away. The formula for the potential energy isn't likely to be something simple, say involving the square of Q as for the perfect spring. To solve this problem, we shall have to make an approximation to the true potential energy function. And this will involve the use of a Taylor expansion. Now, so far as our pendulum is concerned, the only purpose of this string is to ensure that the bob moves in a circle. So a method which applies to the pendulum can also be applied to any particle which moves along a curved path, such as this toy car. It's friction that dampens down the motion. But we're going to leave damping to the next unit. So what is it that drives the oscillation? David?
Well, instead of a spring as our source of potential energy, we'll be considering gravitational potential energy. Now, you know from Unit 4 that when a particle falls vertically, it loses gravitational potential energy. And the same thing will happen here. On the way down, the kinetic energy will increase as the potential energy decreases. Now, at the bottom, the potential energy is a minimum, and so that's where the kinetic energy will have its maximum value. And on the way up, of course, the kinetic energy will decrease as the potential energy increases. Now, the car almost gets to its original height. Not quite, because of friction and air resistance, which also plague real spring mass systems, as opposed to Allen's perfect ones. Now, the same interplay between gravitational potential energy and kinetic energy will occur on any shape of track. The details of the motion will clearly depend upon the shape of the track. And I'm certainly not claiming that that is simple harmonic motion. But near to any minimum of potential energy, like this one, the oscillations don't look very different from what we saw with the spring. So, how can we use energy conservation to predict what will happen near to a minimum of potential energy? And what sort of motion do we get?
Well, let's generalize what we did for the perfect spring. Suppose I have a particle whose position is described by just one variable. Now, that variable could be the length of the spring, for example, or perhaps the distance along one of David's curved tracks. Well, in that case, the energy conservation equation is just kinetic energy, a half m the speed squared as usual, plus u of q, which is the potential energy function. Now, David tells us that we're interested in what happens near a minimum of u of q. Now, what do we mean by a minimum? Well, by definition, if u has a minimum at q0, then the first derivative is equal to 0. Well, in fact, that could be a minimum or a maximum, but it really is a minimum if the second derivative at q0 is positive. Now, let's use these conditions to find a nice approximation for this potential energy function near the point q0. Well, I'm going to do this by means of a Taylor's expansion. So, I have a first term, a constant term, which is u of q0. And then I have my linear term, which involves the first derivative. Then I have a second derivative. And really, I'm going to stop here. So, in fact, this is only approximately equal. I'm neglecting the higher terms. Well, it still looks a bit complicated, so let me simplify. First of all, the constant term. Well, I can choose the potential to be 0 at the minimum point q0. Remember, that's what we did for the perfect spring. So that gets rid of the constant. Now, the first derivative, well, at a minimum, that's 0 anyway. So this term goes out. And in fact, I'm simply left with this rather simple expression for approximation near q0 in terms of this second derivative only. Well, where have we seen something like that before? Well, if you compare the energy conservation equation for the perfect spring, you'll see that it's precisely the same form as our approximation, except I've written q in place of x. Well, that's very interesting because it tells us that in the general case, we've got approximately simple harmonic motion near the minimum q0. In fact, if the potential energy function u of q were perfectly quadratic, then this would be exactly equal, and we would have exactly simple harmonic motion. But as I say, in the general case, when it's not quadratic, it's just an approximation. Well, that's interesting, but we can even make a far more interesting prediction, because we can find out from this expression what the period is. Remember, the period for the simple harmonic motion is just defined as being 2 pi over omega, where omega is the angular frequency. And the angular frequency is given by the expression root k over m, where m is the mass. And what is k? Well, if we compare expressions again, k is just the coefficient of this term. So in our case, it's just got to be the coefficient of this, which is the second derivative. So in fact, we have this equality, and that gives us a very general expression for the period of this simple harmonic motion near a minimum of the potential energy function.
Okay, so let's apply this result to the case of the pendulum. Here are the formulae that Alan has just established. Period is given by this, where omega is root k over m. And provided the potential energy at q naught is 0, k is given by its second derivative at that point. Well, what's q naught? It's the value of q where the potential energy is minimum. In other words, the value of q at the lowest point of the path. But we chose just this lowest point as the origin for q. So in this case, q naught is actually 0. I have to calculate the gravitational potential energy of the pendulum, u, in terms of q. First of all, where shall I take the datum level? Well, I'm going to take the lowest position of the bob as datum, because if I do, u of q naught, which is u of 0, will certainly be 0. The next thing is to find a formula for u. If I take the lowest position of the bob as datum, this distance is h. So u of q is just mgh of q, where m is the mass of the bob. In this formula, I've written h of q to remind us that h must be expressed in terms of q. So what is h in terms of q? Well, the easiest way to find h is to start by finding it in terms of this angle. Now this distance is L, so this distance is L cos theta, and h is just L minus L cos theta. I've taken out the L as a factor here just to make life a little bit easier. Now q is L times theta, and so I can rewrite h as L into 1 minus cos q over L. So now I've got h in terms of q, and substituting in the u expression will give me this for u. Now to find k, I have to find the second derivative of u. If you differentiate cos twice, you get minus cos. But you also have to take into account this L here. Each differentiation introduces an overall factor of 1 over L, so that's 1 over L squared altogether. The constant term goes away, so finally I get this for the second derivative. The next thing is to put q equal to 0. Now cos of 0 is 1, so k is given by this, mg over L. Now omega is root k over m, and that's root g over L. So finally I get t, the period, is 2 pi root L over g. Notice that the period doesn't depend on the mass of the bob. So to fix the period of a pendulum, all one has to do is to choose the right length. In fact, for a period of 1 second, the length has to be just under 1/4 of a meter. So by adapting the method of conservation of energy, we've been able to find a nice simple formula for the period of a pendulum.